and this question is asking us to find the v-vector that minimizes the following objective listed here, given that the a-vector is this. So we have to show how taking the derivative of the objective function achieves the optimal solution. So first, we would differentiate. So this just involves finding the derivative of the objective function and setting it to 0. So we can write it as so, over tv of v t a v minus lambda of v t v minus 1 equals 0. So I just copied the objective function and put a derivative around it. So the derivative of VTAV would be 2AV, and then the derivative of this would just be 2 lambda V. Since this is just a unit vector, so it just turns into V. After that, you combine the two, so 2AV minus 2 lambda V equals 0. So that would just be 2AV equals 2 lambda V divided both by 2, so you can just cancel these two. So AV is equal to lambda V. So from here, you will see that this is just an eigenvalue problem, with lambda being the eigenvalue of A, and V is just the corresponding, eigenvector. Sorry for my handwriting, it got a bit close to the edge of the screen. Anyways, so this is just an eigenvalue problem, so we can solve it as such. So this is the second part of the problem, so it's just an eigenvalue problem. So you would just solve the polynomial of the determinant of A minus lambda I equals 0, where I is the identity matrix. So from above, A is equal to 4, 1, 4, 1. Oh, no, sorry. 4, 1, 1, 4. So we can use that here. So the determinant of A minus, just A minus lambda times the identity matrix is just equal to 4 minus lambda, then 1, and then 1 and 4 minus lambda. Because A is equal to 4, 1, 1, 4 over here, and lambda times the identity matrix, so you just subtract the 2. So therefore, we would just get 4 minus lambda times 4 minus lambda minus 1 times 1. So that is just equal to the determinant of A minus lambda I. So from there, we can just take this equation and simplify it out. So from there, we would just do some simple multiplication. So it would be 16 minus 4 lambda minus 4 lambda plus lambda squared minus 1. So you simplify that all out, it would just be lambda squared minus 8 lambda plus 15. And to solve this quadratic out, you would just do lambda minus 5 and lambda minus 3. So that would all equal back out. So therefore, the two eigenvalues you'd find are just to solve this equation. So the eigenvalue would be equal to 5 or 3. So that's your second part of the problem done. So once you find the eigenvalues, you go back to the problem and you see that this is a minimization problem. And since the smallest eigenvalue you find will always minimize the function, you choose 3. So this is min. If the problem asks you to maximize the function, you would choose eigenvalue of 5. So this would be max. But since we're solving the minimum, we don't need the max, so you should just not solve for that. So we can just go to a new page here. So now we just solve with the eigenvalue of 3. So for eigenvalue, so for lambda equals 3. So you would solve the same function. So you would solve a minus lambda I of v equals 0. So you would solve this. So you can just substitute lambda right in, and just for reference, a is equal to 4114. That's just given in the beginning of the problem, so you can just solve all those in. So it would be 4114 minus 3i times v equals 0. So all this right here would equal 4 minus 3, 1, 1, and 4 minus 3. Since it's the identity matrix, times, and you can just expand out this v vector to v1 and v2 equal to 0. So this would just be 1, 1, 1, 1. V1 and v2 is equal to 0. Okay. So once you do this, you can just multiply it out. So you just take this here and wait 1 second. I do not. Let me just take this out. That was not right. So you just have to multiply it out. So it would just be v1 plus v2 is equal to 0. And then v1 plus v2 is equal to 0. So you have the system of equations from multiplying the above step out. So once you do that, it's pretty obvious that v1 is on top of 1. Would satisfy the eigenvalue. For lambda equal to 3. So any vector of the form of this form would satisfy the this should be eigenvector. I'll just rewrite that. Apologies for my handwriting again. So once you find this, you are going to have to normalize this vector, which is pretty straightforward to find so we can just kind of go to a different page here. So the norm of -1, 1 is just going to be equal to the square root of the top value, -1 squared, plus 1 squared. So that's pretty straightforward. That's just going to be equal to √2. So therefore, this vector is just going to be equal to 1 over √2 of -1 and 1. And yeah, this will be the vector that would minimize the object for the